All right, guys, over the last week we've discussed data organization, and now it's time to move on to some of the elements of assembly language programming. So let's start with a discussion of the different types of statements. There are three that the book mentions in particular, and it is these three. So let me just talk a little bit about them. An instruction is a statement that's translated by the assembler into one or more bytes of object code or machine code. Each of these is recorded at execution time, or runtime. An example might be, any of the examples that we've talked about in class. So move value to EAX as an example. A directive. A directive is a statement that tells the assembler to take some action but does not result in machine instruction. In other words, it has no effect on the object code that's going to be running. Examples of this that we will see include things like dot 586 or dot model flat. Whoops. Not all directives start with a dot. It's just those two come to mind. I'll show you when we go over this first example. We'll talk a little bit more about all the different types of directives. A macro is it's easy to think of it in the same way as a function. It's not. When you write a function, it is a piece of code that is written once and called multiple times. But a macro is shorthand for a sequence of other statements, whether they are instructions, directives, or even other macros. Every time a macro is called, that sequence of statements is inserted in the executable code. So it is the code itself is copied multiple times instead of a call to a function. So that's the difference. So an example for this would be something like an input macro. Input prompt. So this is where we prompt and read. Where would we put it? We'll put it string up to 40 characters. Okay. Again, I'll show you all of these input and output macros. I also wanted to include, though, in this a discussion of comments. Comments are critical, and we will see comments throughout. They're especially important in this class, however, because, and I'll give you an example. A comment in assembly language is going to start with a semicolon. Unlike ending a C++ instruction. Comments are important. We'll talk a little bit more about those in just a second. But before we get started on more of a discussion of how to use these things or syntax, let me highlight those things that we've just talked about. So you see right here there are a bunch of semicolons at the beginning of these statements. These are comments. They will not be included in the executable code at all. You see a lot of things that start with a dot. Those are directives. But in addition, here's a directive. This directive actually allocates memory for us. We also saw comments over here. I've got instructions here. This particular one doesn't have any input and output, so I can't show you that. Gives you just some ideas, though. Okay. Again, though, let's look at some syntax before we dive into that a little bit. A typical instruction is going to have 3, maybe 4 areas. The first one is the name or the label. It is optional. It ends with a colon, as you see right here, and used with an instruction to symbolically reference an address in memory. And I'll show you an example just after we finish our discussion of the different pieces. where this makes sense. It is used as a place to jump to, if that makes sense. So it's not going to result in executable code. It's just a marker in memory that says, oh, when you jump to this label, here's where you go. So first part is the mnemonic. This is like add or sub or move, any of those things that we've looked at. This indicates a specific instruction, directive, or macro. Operands. For instructions, various instructions will have 1, 2, or more operands. Some instructions will have 0 operands. Many macros that we'll use have up to 3 arguments in the list. And then finally you see comments. Okay, so I'll point out once again the importance of a comment after every assembly language instruction. So let's talk a little bit about programming styles since we've just looked at the instruction. Opcodes are not case sensitive, but be consistent. So let's just say be consistent in use of case. You can say add something to something. You could also say add something to something, but be consistent, whatever you do. Most of the times, I'll tell you, for opcodes, I use lowercase. For labels, I'll use uppercase, just to make the code a little bit easier to read as I go through it. Second thing, we want to make sure our code lines up. Again, readability in assembly language is even more critical than it is in a high-level language. High-level languages are easier to read, assembly language not as much. So let's line it up. So use tabs. Okay. Comments. Let's talk a little bit more about comments. You've got to include comments after every instruction in assembly language. But more importantly, the comments must explain how your program works, not just what the program or what the instruction is doing. Okay? So let me show you an example. Let's say we have something like this. Here's a label. Compare EAX to 100. Let me just write the code, and then we'll fill in with some comments. If EAX is greater than 100, we'll jump to done. Add EBX to EAX, and then jump back up to top. We'll put done down here. We don't know what we're going to do at done, but it doesn't matter. We're just looking at an example here. So for this one, let's say something like I want to compare to an upper bound. So compare total to upper bound, whatever that might be. And again, knowing what you're doing makes your comments a lot more meaningful even than these. So here would say if total greater than upper bound, we're done. Else, add value to total. And finally, loop again. So these are just some examples of comments that do something more than just, again, sort of regurgitating what the instruction's already doing. Okay? All right. Moving on. With respect to bytes, I need to talk a little bit about how these bytes are actually stored in memory. Okay. So in this example, we are asking by the instruction, we want to store our results, which are in EAX. We want to store them in a place in memory associated with the identifier sum. So here's what you might suspect. Let's suppose that EAX has this value in it. And I am, just by looking at this instruction, I look at sum. I don't necessarily know what size it's referencing in memory, but EAX tells me this is going to be a 32-bit move. So, since that's the case, I am automatically going to go to sum, assuming it's here, and look at a 32-bit value that it's pointing at. Here's where this gets a little bit tricky, okay? What you'll notice, I have moved EAX into sum, but it's not moving. I think I might have expected it to go like this. And that's not how the Intel x86 family of processors stores byte information. It actually stores it in Little Endian, also known as reverse byte ordering. Little Endian. So this is from Gulliver's Travels, if you've ever read Gulliver's Travels. So let me talk a little bit about that. It takes, remember for Little Endian, a couple of things that are important. Let's just rewrite this. Little Endian, also known as reverse byte order. To satisfy Little Endian, you have to be storing a multi-byte, so more than one byte, scalar value or numeric value in memory as opposed to a register, for example. All three of these conditions must be met in order for anything to be stored in Little Endian. Okay? Since I am moving a multi-byte scalar value into memory, it's going to go in reverse byte order. So what that means when you see multi-byte scalar value being stored in memory is the least significant byte will go in the smallest address. The next least significant byte will go in the next address, and so on and so on. Okay? So you say, gosh, that's kind of confusing. It is, but it kind of makes sense. And here's the deal. Designers can determine whether their processor is going to be big endian or little. So you say, well, which of them do they choose? Well, it depends on what they want the machine to do. So you see a lot of discussion about the relative merits of the two formats, very similar to the religious arguments in Gulliver's Travels. The bottom line is there are some advantages for big endian that we see right here. There are also some advantages for Little Endian. So in kind of the essence, Little Endian form, instructions for picking up a 1, 2, 4 or longer byte number proceed in exactly the same way for all formats. First pick up the lowest order byte at offset 0 and so on. Also, because of the one-to-one relationship between address offset and byte number, in other words, the offset 0 would be byte 0, multiple precision math routines are easier to write. That's Little Endian. In Big Endian form, having the high order byte come first, you can always test for whether the number is positive or negative by looking at the byte at offset 0. You don't have to know how long the number is, nor do you have to skip over any bytes. It also makes binary to decimal conversions a little bit easier. So again, it depends. For now, realize that when we store multi-byte scalar values in memory, they will be stored in Little Endian or reverse byte order. We'll practice a little bit more with that because it does take a little bit of getting used to. This next example we're going to go over or through in class, as well as the list file. So for now, let's stop it there, and we'll pick up with constant operands next time.